Continuity in generalized binary topological spaces. Well, binary topological spaces have been introduced by Jyoti Tangavelu, as we already know from our earlier videos. Later, this idea has been reproduced in generalized framework by Tivagar and Kavita, by Mustafa Jamal, and by Iyengar, Maitra, Chaturvedi, and Sharma. These are three independent approaches. Moreover, Setalakshmi and Kamaraj founded N-Airy spaces which are extension of binary topologies. And we also had presentations about N-Airy spaces. As for the generalized topological spaces, they've been studied by many authors, but perhaps the most important of them was Ákos Csásar from Hungary. And the following definition is repeated after Csásar. As we can see, the whole idea of generalized topological space is that the empty set should be open and we should have closure under arbitrary unions. The whole universe may not be open. If it is, then we say that our generalized topology is strong or supra. Well, according to Jamal Mustafa, generalized binary topology can be defined in the following way. Let X and Y be any two non-empty sets, universes, and generalized binary topology from X to Y is a family mu B contained in the product of power sets, and that satisfies the following actions. Empty set, this pair is open, generalized open, and again we have closure under arbitrary unions, not necessarily under finite intersections. And of course the notions of union, intersection, and so on are defined component-wise, just as always in binary spaces. This was in our preceding presentations. Well, one can add that Iyengar and al., Iyengar with his cooperators, they assume that the whole binary universe is open, so their generalized binary topology is always supra, always strong. The same assumption has been made by Tivagar. However, Jamal Mustafa does not require this condition. Hence, we think that his idea is more general and maybe even closer to the original concept of Csásar. Just as in the case of ordinary binary topology, it's possible to prove that the concept of generalized binary space is independent from the idea of generalized product topology. Moreover, one can prove that if we have a family of strong or not strong generalized binary topologies from X to Y, then their intersection is also another generalized binary topology. However, this doesn't work with union. Yes, union of some generalized binary topological spaces need not to be a generalized binary topology. This is a counterexample. Yes. Well, you may check that these families are generalized binary topologies. However, their union is not a generalized binary topology. Consider these two sets, this one and let's say this one, and their union, which won't belong to this union of these topologies. Well, another example of strong, in this case, generalized binary topological space is here. You may meditate upon it for a while. Then we say that AB is G binary closed, generalized binary closed set, if its complement is generalized binary open. This is typical and standard. What about continuity? Assume that X, Y with generalized binary topology mu B, that we have such G binary topological space, and moreover we have ordinary generalized topological space, yes, not binary but with one universe, and we define we say that a function from this a mono universe from Z into a product of X and Y is called G binary continuous at Z, which belongs to capital Z, if for any G binary open set AB, which is open in XY, such that f of Z belongs to AB, there exists a G open set G in our initial universe Z, open with respect to the generalized topology tau, for which Z belongs to G and f of G is contained in AB. Well, we say that function is called G binary continuous in general if it is G binary continuous at each Z in Z. Well, this is equivalent, one can prove, with saying that pre-image of AB is G open in Z tau for every G binary open set AB. So this definition and this theorem here is standard, yes, as one could expect. The notions of generalized binary interior and generalized binary closure are also standard and modeled after typical topological spaces or typical generalized topological spaces. Some details are here, as you can see, but you may think that generalized binary interior is just the largest binary G-open set contained in our AB. Of course, inclusion is defined component-wise, as it has been shown in our earlier videos. Now we may introduce several other forms of, let's say, openness in our generalized binary spaces. And these notions are based on the well-known definitions from the theory of ordinary topological spaces. We have semi-open sets, pre-open sets, alpha open sets, and regular open sets, and their definitions are based on the notions of generalized binary closure and or intersection. Yes, here we have inclusion, 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 and here we have equality. One can prove that, of course, every binary generalized regular open set is binary generalized open, and on the other hand, every binary generalized open set is alpha, semi, and pre-open. But now we have something interesting, because we may easily imagine the corresponding definitions of continuity. And these definitions are taken from Jamal Mustafa. Well, note that in each case, we expect that pre-image of semi-open set in case of semi-continuity, pre-open set in case of pre-continuity, alpha open set in case of alpha continuity, and regular open set in case of regular continuity, that it will be not semi-pre-alpha regular generalized open in our universe Z with generalized topology tau, but open, G open, G open, G open, and G open. This is not a mistake. And this is a strictly different approach than the one presented by other authors, like Hanger et al. So you should compare their results because Jamal Mustafa proves the following theorem in his setting. In this setting, we can say that every binary generalized alpha continuous function, for example, is binary generalized continuous. And the converse is not true in this setting. And this is quite atypical. Yes, here is a counterexample. You may think about it, you may analyze it, and finally you can see that pre-image of this is equal to the singleton of P, but this set is not generalized open in the topology tau associated with the universe Z. So this is quite specific, yes, because other authors require that, for example, function is called binary generalized semi-continuous if pre-image is semi-G open in Z for every binary G semi-open set and so on. So an interesting area of research. Here is our bibliography, our references. So thank you very much for your attention.